I'm Holly, and I work on Swift at Apple. Today, I'll talk about bringing data race safety to a mainstream programming language used by millions of programmers. And this is a story about adapting many years of PL research to improve the lives of everyday programmers at scale. Swift is a natively compiled, general-purpose programming language that aims to be safe, efficient, and expressive. Approachability is important to us. You can use Swift from your very first line of code all the way through to your professional software engineering career. We want to design a language that people want to use, a language that lets people express their ideas without the language getting in their way by bogging them down in extra ceremony. Often, when folks talk about memory safety, they focus on the security benefits. Security is important, but memory safety is also an important part of being productive in a language. A single use after free can lead to multiple days of debugging. That's hard on anyone, but especially so on beginning programmers. With memory safety, there are a lot of solutions that are ergonomic and safe, and Swift has been memory safe by default since its launch. Concurrency safety has been a harder problem. We needed to provide safe concurrency because data races undermine memory safety, and they make concurrent programs notoriously hard to write and maintain. A concurrency model in the language, with safety guardrails from the compiler, can help make concurrent programming approachable to everyone. When we introduced our concurrency model into Swift a few years ago, we drew inspiration from the actor model popularized by Erlang and Scala. Each actor executes sequentially, processing messages it receives, and sending messages in return. There can be many actors in a program, and they all execute concurrently with each other. Actors suit Swift really well because Swift already provides support for object-oriented programming with classes. In the traditional actor model, actors are generally in different processes or on different machines, and the messages are always serialized when they're sent. Swift does support this via distributed actors, but in Swift, most actors exist within the same process. Swift actors pass messages through function calls, like this call to greet, and they await the results using the language's async await feature. Swift's concurrency runtime will suspend the caller if the actor is busy, allowing it to scale to large numbers of actors in concurrent tasks. Because actors are in the same process, we don't have to serialize data when we call across actors. We can pass the arguments in the same way we would for a normal function call, which is much more efficient. And this works great for types with value semantics, like integers, strings, and arrays of values. But being in the same process introduces some problems if you have shared mutable state. The language model assumes the existence of an underlying thread system, and any concurrently executing tasks can execute in parallel at runtime. Let's say that instead of passing strings from one actor to another, we're passing an instance of a class. As in many object-oriented languages, classes in Swift are reference types. So actor A has a pointer to an instance of the person class. When actor A calls actor B, it carries with it that pointer, and now we have a problem. Two actors that can execute concurrently both have pointers to the same mutable state. While actor B is running greet and accessing person.name, actor A can run a concurrent task that modifies person.name. This is the textbook definition of a data race. So we needed an approach that made sure that safe values, like integers, strings, and arrays, can be shared across actors. But mutable state without synchronization, like class instances, are prevented from leaving the actor in which they're stored. Rust had a good answer here with its send trait, which we adopted as the sendable protocol in Swift. Only sendable types can be sent across actor boundaries. Think of it like a barrier around the actor encompassing its mutable state. We specify that value types, like ints, strings, and arrays of sendable elements, are sendable because the data is copied, which means that it's safe for them to slip through the bars to be used in a message to another actor. But if you try to send a message containing a non-sendable type, like an instance of a class, Swift will reject the call so that mutable state stays within the same actor where it's safe. This means that the compiler will reject a call that passes an instance of person across actors to prevent the risk of concurrent access to shared mutable state. This is a good model. It provides data race safety, and it's reasonably easy to explain. We even made Swift available with optional data race safety checking based on this model so programmers could try it out and improve their use of concurrency. But as programmers tried out this model in their code, they discovered a serious expressivity problem. That jail that provides data race safety for actors is very strict. Consider this code. It creates a person and a dog instance, creates references between the two objects, and then it initializes a new actor. This code is free of data races so long as it doesn't touch the Laura or Daisy instances after it creates the actor A. But Swift would reject this call because class types like person or dog are not sendable. We looked around, but none of the existing solutions worked for us. An ownership model based on linear types is too limiting because it prohibits arbitrarily complex object graphs, which are the right way to model many problems. And we don't think programmers should have to write a natural code to get the data race safety guarantees, especially in code that doesn't use concurrency. Essentially, we were stuck. We had a safe, explainable model, but it rejected too many programs that were actually safe from data races. Fortunately, this paper on a flexible type system for fearless concurrency was presented at PLDI that year. It proposed a new type system that could provide data race safety for object graphs with minimal annotation burden on programs. This research had a pragmatic approach to provide safety without sacrificing productivity for programmers, which sounded like exactly what Swift needed. We collaborated directly with two of the authors, May Milano and Josh Turcotti, to determine whether this model was suitable for Swift. The type system uses regions to track disjoint subgraphs of the object graph. The key insight is that linear types can be applied at the region level to allow complex object graphs to be formed and used within a single thread, and the region is consumed as a unit when any object in the region is sent to another thread. Regions are a conservative approximation at compile time of the runtime object graph. Any operation that could possibly introduce a path between two objects must consider those two objects to be part of the same region after the operation. If a thread has two regions and it sends an object from the second region to another thread, all objects in the second region are no longer usable from the original thread after the send operation. This allows complex object graphs to be sent across threads while maintaining mutually exclusive access to mutable state. Instead, if you create a reference from one region into another, the regions get merged into one large region that can be transferred as a whole. We adapted these ideas and we proposed them for Swift. This is the written proposal for Swift's open source language evolution process, and the proposal is implemented in the Swift 6 compiler that was released in September of this year. There are a lot of interesting adaptations that we made to fit the type system to Swift's concurrency model that I won't get into, but I'll walk through a few simple code examples to demonstrate the expressivity win. The Swift compiler tracks regions within function implementations. Every actor has a region containing its mutable fields, and objects in actor regions can never be sent to another actor. Actors can also contain fresh, local regions that are formed by constructing new object instances. Swift reasons about method calls and field assignments to merge regions. Methods and accessors can form or keep references to their arguments and result values, so all arguments and results are merged into the same region by default. Only values with non-sendable type are included in region analysis. Values with sendable type, like strings, are not included in regions because these values are always safe to pass across actors. As long as a non-sendable object remains in a region that is disjoint from an actor's region, it can still be sent to another actor. Forming new actors and calling methods across actors are the send operations in Swift. It's safe for the Laura object to be used to initialize a new actor instance because its region is disjoint from other actor regions, so the objects are not reachable from any other actor. If the programmer sends an object across actors, the region associated with the object is merged into the actor's region. The code is safe as long as you don't try to access any object in the region after that. And if you try, you'll get an error message showing where the region was consumed and the subsequent use of the region, which is where the risk of concurrent access occurs. These default region analysis rules apply with no additional annotations in the program. The person and dog classes look like any other class in Swift with no concurrency-related annotations. The default rules for region merging allow the adopt method on person to store a reference to the dog argument, just like programmers would expect. And these default rules work well for most code. But programmers can still explicitly specify that specific argument values or a result value is disconnected from the other arguments and results. For example, if I have a cat distribution system class, the next method that generates the next cat to go and select its new owner should return a value that isn't in the same region as self. I can express this using the sending keyword. This indicates that the result value is in a disconnected region, and in the caller, it can be sent across actors independently from the other values in the call. This is checked by the compiler, which will reject an implementation of the next method that returns a value that's already in the same region as self. The sending keyword doesn't give programmers precise control over all regions in a call, but we found that a simple keyword on individual values is sufficient for what programmers need to be able to express. But this was a trade-off between expressivity and the language complexity that would come with adding full region variables to function signatures. This region-based concurrency model is a massive simplification for programmers. It's an intuitive model that allows many natural, data race-free patterns to just work. Regions have no visible impact on code that doesn't use concurrency, maintaining progressive disclosure for programmers who haven't yet learned about concurrent programming. But there was one more problem. We have a data race safety model that adds new restrictions in concurrent code, and now we need to integrate it into an existing ecosystem of Swift projects. There are millions of Swift programmers today with large code bases, including dependencies that they may or may not own, all of which was written before we enforced data race safety. Migrating existing code to the new model takes real engineering effort, and requiring all code to change at once is impossible. We had to design an incremental rollout plan for the entire Swift ecosystem. When you're introducing a new feature into an established programming language, the rollout plan can be just as important as the design of the feature itself. It doesn't matter how good your feature is if programmers can't use it. For Swift data race safety, the incremental rollout is based on the idea that any module should be able to adopt data race safety and see the benefits without changing other modules it depends on. The Swift compiler will introduce runtime checking at the boundaries between data race safe and unsafe code to detect data races introduced by the unsafe code. This runtime checking is temporary, and it will go away when both modules statically enforce data race safety. So the system trends toward fully static data race safety over time. And finally, there are suppression mechanisms that silence concurrency-related error messages for code that you don't own, so that you're never stuck waiting for a dependency to update before you can adopt data race safety. Data race safety is a hard but incredibly important property for a programming language. Swift has benefited from decades of PL research to introduce this property, from actors and linear types to region-based isolation. Our experience in adapting research to a mainstream programming language taught us how crucial it is to fit an idea to the existing language and ecosystem. We simplified the ideas from the fearless concurrency type system down to something that we could teach and something that fit the language where it was. And even after we had a design we believed in, we weren't even close to done, because the rollout of this feature is what will ultimately determine if we have succeeded. I want to especially thank Josh Turcotti and May Milano for working with us to adapt their type system to the Swift language. It's going to make a huge impact on the Swift programming community. And we're interested in continuing collaboration with researchers, especially in areas that hold programmer productivity as a key goal. Thanks for listening.
I'm fascinated, especially about the fact that you added this to a language that had already been designed without any of this in mind. And I'm wondering what the, and of course I'm curious about whether it could be added to other languages that already exist that also don't have any of this in mind. And I'm wondering what the prerequisites are for a language to be a suitable starting point. In particular, a language, let's say like Scheme, that has pure lexical scoping, sound reasoning about scope, no sound static type system, does the kind of types and static analysis you're bringing leverage a pre-existing conventional type system, or could it be added to a language like Scheme, which is statically scoped, dynamically type safe?
That's a good question. I think a lot of the rules, at least in the data race safety model that we have, do leverage the static type system. Like, one of the huge benefits of adapting this region-based analysis into Swift is that The static guarantees we already had around sendable provide a way to create smaller regions, and every time a type becomes sendable, you end up having more regions in your code, which ends up allowing your code to be more expressive. So I'm not familiar enough with Scheme to say whether or not that's something that could be adapted to Scheme, but I definitely think the lessons that we learned around having the incremental rollout plan would be crucial to try to adapt new safety into an existing established programming ecosystem.
Okay, and one more question. Did any of this involve new runtime mechanism, or is all of this new static analysis erased before runtime?
All of the static analysis happens before runtime. Swift's concurrency system in general does have new runtime support, but the data race safety side is entirely static.
Okay, thank you.
Yeah, thanks for a really interesting talk. I've tried to get my head around what Swift was doing in this space, and it was the first presentation I've seen that I managed to understand, so thanks for taking pity on an old man. One of the things you said was when you use your sendable, whatever it's sending annotation, you return an object, you can hand it on to another actor, and then you said the new object's region is merged into that of the actor. Is that actually the full story? That to me would mean, for example, that an actor, the receiving actor, couldn't then send the object it had got onto a third party.
Yeah, so the same annotation works on function parameters as well, so that you can annotate the parameter on the receiving actor to allow the actor to transfer it further to somewhere else.
Great. Okay, so based on Amanda's talk, this really is external uniqueness then.
So first of all, thank you. This is really cool. It's great to see these technologies being integrated into industrially relevant languages. I'm curious in understanding a little more about how sendable works, and maybe I didn't understand everything you said, but it sounded like you said that, first of all, arrays are sendable if the component is sendable, and that works by copying. And so I wonder if there are performance implications that people should be worried about.
Yeah, all of the collection types in Swift specifically are copy on write. So that they have been since the initial release of Swift. But Swift really heavily leverages value semantics, sorry, for both structs and enums as well as the collection types, and the data race safety model you can really leverage that, because when you have value semantics, everywhere you pass that data, you have independent copies. I don't think we've seen in cases where creating a copy would have serious performance implications on your code. Those are the types of cases where you would reach for classes instead. But classes have different performance trade-offs, like memory allocation on the heap, for example. So I don't think there's like one solution that works for all code. Yeah, I don't know if that specifically answers your question, but that's mainly how sendable works. The compiler can automatically validate you write a conformance to sendable in the same way that you would declare, like implement a trait in Rust, for example, for Swift, and the compiler will infer that for very simple value types like structs that only contain other sendable types. But you can also, if you have a class that can't be subclassed and only has immutable fields, that class can have a sendable conformance as well.
Okay, so immutability allows you to be sendable without copying.
Fully structural immutability all the way down is what. So it's a property of the type. It's always safe to have a concurrent reference to that type, and any operation that you do on that type can't introduce any data races.
Awesome, thank you.
Yep.
Okay, so I wanted to ask you a question about the slide that's right before this one. So you said that you protect code at module boundaries with runtime checking, and then you also said that you have suppression mechanisms for issues. So now my question would be, so if you introduce, are there some guarantees that you can't ensure with runtime checks, or are these suppression mechanisms just disabling the runtime checks for performance benefits? Mm-hmm. Or like how do these two interact with one another?
So the runtime checks are not comprehensive. Swift also interoperates with C family languages, so you can, we don't actually like fully check that, everything you can do on the C side isn't introducing any data races. The runtime checks are specifically there because the compiler will rely on some annotations in function signatures. Like a sendable is actually an example. Like it can rely on a conformance to sendable. You can also annotate function types as sendable, which means everything the function captures has to also be sendable. And in cases where that's not there, the compiler will assume that that never escapes the actor that it's formed in. So those are specifically the cases where the runtime checks are inserted, so that when a function is called, if the compiler had made an assumption that it can never be called across actors, the runtime check is there to assert that you've called the function on whatever actor the compiler expected you to call it on. So the runtime checks definitely are not comprehensive, but they do catch the cases where the compiler had made some assumption that was then violated in the implementation of your library. But the suppression mechanisms for code that you don't own is mainly for cases where there's not a conformance to sendable in a specific type that you're using, but you believe that there should be. Like maybe in the documentation it says that some type that you're using is fully thread safe. And that's not specified by the library. You can choose to suppress that warning. It's something that you write on an import statement, and then later on when the library is updated to have static data rate safety, those warnings will come back then, so you can no longer continue to ignore something that was not fixed in the library when the library author has said, no, this has been fully updated for static data rate safety. If there are any issues that are not fixed, the client can no longer ignore those. They'll come back as warnings.
Any more questions? I have one more question. So, in your region system, you are inferring the regions automatically, and you're basically piggybacking on your static type system and the sendable. And so, one of the points you made was that you don't need to put any explicit annotations into the code, right? And so, and here is a point where I know that I and Milano do agree, because I like my annotations in the code. I like the code to sort of explain what it's doing. So, can you expand on the thinking there? Is clearly the regions are there. If you violate the regions, you're not going to be able to compile your code. But the regions aren't visible in the code. Why is not putting annotations in the code a good thing?
Yeah, I think a property that we really value that I mentioned is this idea of progressive disclosure, so that programmers don't have to care. If they're just writing single-threaded code, why should a programmer have to confront this idea of regions? It's only at the point when they've made a mistake that regions are really important. And the compiler does try to point out the different areas in your code where something happened to merge the regions, for example. And we also, we do think it's valuable for programmers to be able to have that insight at the point when they need it. And some sort of visualization tool for seeing the regions in your code, I think is something we would be really interested in, so that programmers can explore the regions if they need to. But if they're not using concurrency and they're just writing single-threaded code, it doesn't matter if everything's in one giant region, then programmers don't need to care.
Right, and I agree with that. But as soon as they opt in to concurrency, it seems to me that it would be a nice idea to be able to at least explain to someone who comes along and reads the code, where are my regions? How have I organized my data so that I can send it as I'd like? But we can take.